Hello everyone, I hope that you are doing good. Welcome to another lecture of robotics. So today's lecture is about the kinematics of robotic manipulator. So what is a robotic manipulator? It is a robotic arm which is mostly used for industrial purposes. So you can use it for multiple tasks, for example for the painting, welding, and for grasping or manipulation. So in this lecture we shall discuss about the kinematics of the robotic arm. So what is kinematics? Kinematics is the study of motion without considering forces that causes motion. So whenever we talk about motion of anything, any object, any rigid body, let's say this is the point here, P point, and this point move from this location to this second location, which is P dash. So the distance traveled by this point can be calculated if we know the velocity of this point and the time it takes to reach here. So we can calculate S is equal to V cross T. So this is the new location of this point, and this is an example of kinematics. Because we haven't considered the forces acting on this particle or point, we haven't considered friction or any other force acting here. So let's take another example where we have a circle, a wheel, and the wheel initially was at this location, and after that it traveled to this location here. So this is, let's say, the C1, then we have C2, another location. So so the total distance traveled can be calculated if we know the number of revolutions of this wheel into 2 pi r, where r is the radius of this wheel. So this is again an example of kinematics without considering the forces acting on this wheel. Let's take one more example here. We have an x coordinate and y coordinate, and here we have a pendulum. Some sort of pendulum, and this the point is located at, the end point is located at point P, and what we want to this angle theta is known, and what we want to find is the location of this point, the xy coordinates, where they are located. So how can we do that? We can use kinematics because there are no forces involved. So this will be your x coordinate, small x here, and this will be your small y. Okay, so your x will be equal to, okay, let's say that the length of this point is L. The distance from origin is 0, 0 to this point. Let's say this is L. So L is equal, x is equal to L cosine of theta, and y is equal to L sine theta. So this is how you can calculate the final position of this point in xy coordinates. All you need to know is the length, the distance between this point to the origin, and the angle it's making. So this is again another example of kinematics, as there are no forces involved here. Okay, forward kinematics. So here we are talking about, mostly we are talking about robotic manipulators or robotic arms. So what is forward kinematics? Forward kinematics of a robot refers, I think it's a mistake, let me correct it. Robot refers to the, refers to the calculation of position and orientation of its end effector frame from its joint coordinates. So if we consider a robotic manipulator, it looks like we can represent it using some links here. So this is a 2-link robotic manipulator, let's say, and this is link 1 and this is link 2 here, and this is the final, you have the end effector here, the gripper or something. Okay, so what is forward kinematics? Forward kinematics means you have to calculate the position and orientation of this end effector, this gripper, from its joint coordinates, and when the angles of the joints, they are known, theta 1 and theta 2. So if theta 1, theta 2 are known, then find the position and orientation of P. So yeah, so we need theta 1, theta 2, and also we need L1 and L2 also. So yeah, so this is called forward kinematics. So this is a simple example where we have used only 2-link robotic arm having only 2 revolute joints, but there can be multiple links with multiple joints and different types of joints. So yeah, the more joints you have, the more angles you have, the more calculation will be complex. So mostly forward kinematics used in robotic arm simulation. So what happens is that during the simulation of robotic arm, you give it some kind of input, and then your robot moves to that point. Okay, so simulation means you mathematically simulate the behavior of a real robot, and for simulation purposes, if you give the robot some kind of input, so it starts moving, and then it reaches the corresponding location or the position with reference to your input. So forward kinematics is mostly used for simulation. Now let's see what is inverse kinematics. This is again we are referring to robotic manipulator or robotic arm. So inverse kinematics means calculation of joints, coordinates or angles given the position of the end effector. So this is opposite to forward kinematics. In inverse kinematics, what we have to do is we have to calculate the joint angles, but this time the position of your end effector is known. So here we have your end effector and its position is known. Okay, what you have to do is you have to find theta 2 and theta 1. L1, L2. So P xy is known. Find the values of theta 1 and theta 2, and also the L1 and L2, they are also known. So this is why it's called inverse kinematics, because it is opposite to forward kinematics. And yeah, and this is also a little bit difficult and tricky to find the solution as compared to forward kinematics, because there can be multiple solutions. For example, this P point can be reached from another also combination of theta 1 and theta 2, for example from this way here. So that's why inverse kinematics is difficult to find as compared to forward kinematics. Okay, that's what we mentioned in the next slide. Inverse kinematics is difficult to calculate because you start with a desired position and look for a combination of joint angles to reach that position. Inverse kinematics may have single solution, multiple solution, or no solution. So what about multiple solutions? So for multiple solution, for example, let's say we have to reach a point P. Let's say this is a point P here, call it with X. So we know the location of point P, and we have to find the angles that robotic arm has to make to reach this position. So the problem is that there can be multiple options there. For example, a robot can have this configuration and reach your point P, but it can also have something like this configuration and still it's able to reach your point P. So that's why there can be different values of your theta 1 and theta 2, the angles. So that's why they call it like having multiple solutions. So this type of kinematics, we use it for control of robotic arm. Okay, so what you want to do, you want to do a position control. You want that your, let's say, a welding, you are doing welding, and you want that your welding rod should stay on the object, metallic object. Okay, so you want this thing, you're doing welding and you want that your robotic arm should stay here. So this is your end effector. So this, now you're doing position control. Okay, so when you want that your position don't changes or stays at the desired point, so this is a position control problem. So what you need to do, you need to find the angles of the joints theta 1 and theta 2, and you need to control them, these two angles, so that your robotic arm stays at the desired location or the position. So here we use inverse kinematics. Okay, during welding or any other operation, during painting, during assembling, cutting. So it is desired that the position of the robot should be your desired position where you want it to be. And for that you need a specific configuration of your robot. The specific combination of these angles theta 1 and theta 2. So remember that these angles are being controlled by the servo motors or the electric motors in the joints here. Okay, so what you need to do, you need to control the motors that in turn control these angles theta 1 and theta 2, and which finally controls the position P, X, Y, Z in this end effector of this robotic arm. Now let's see an example of a planar robotic arm having two revolute joints. Planar means it's a two-dimensional. For simplicity we are taking it two-dimensional, but we can also, in reality, there are robotic arms having three-dimensional, having X, Y, and Z coordinates. So we take to our robot and try to perform forward kinematics for this. So first we draw the 2D coordinates here. So because this is a planar robot, so we have considered only two dimensions, X and Y. Okay, so now we have the robot here. So this is also a reference frame, and it starts with 0 and 0. So this is your initial coordinate point here. So then we have our link 1. Link 1, we can represent it using different color. Let's make the angle somewhere here. and then here we have a joint, and then we have a link to, because this is a 2R robotic arm, one angle we have here, one joint, and this is joint number 2, and then we have link number 2, and finally here we have the end effector. Okay, and what you need to do, you need to find the position of this end effector, means you have to find the xy coordinates. Okay, so this angle here we have, this angle is, we call it alpha, and then for the first link we define its coordinates, which is y dash, and we have this coordinate is x dash. And similarly we do this thing for our second link. So this is link 1, we call it L1, and this is link 2. So the angle is alpha, and here we also define the x and y coordinates of this point, and this we call it x double dash and y double dash. Okay, one more thing we need to define, that here we know this angle alpha, and here we know this angle beta here. So this angle here is beta. Notice that this angle is anti-clockwise, the angle alpha, and angle beta is clockwise. So this angle beta is negative and angle alpha is positive. So yeah, this is pretty much the 2D representation of the robot is complete. So what we have available is the length L1 and length L2, and also we have angles alpha and beta are known. And how they are known? They can be easily computed using some kind of sensors that can calculate or that can find the angle of the joints. It can be optical encoder or something like that. Now we are interested in to find the final position of your end effector, which is the xy coordinates. So let's see how we can do that. So to calculate the final position xy, first we need to calculate the intermediate positions of, first we calculate the position of this joint, this point here, and which has a coordinate x dash, y dash, and then once we calculate x dash and y dash, then we calculate the position of the end effector with respect to this point here, this joint. Okay, and once we have found that, then we shall add both of them to calculate the final position. So our x dash can calculate using, we have the length L1 and we have the angle alpha, cos alpha. And similarly we can calculate the, so this is x1, x dash, and this is angle alpha. So the value of x dash is cosine of angle alpha multiplied this length L1. Similarly we can calculate y dash, which is L1 sine of alpha. So now we have the coordinates of the intermediate joint. Okay. Once we have calculated them, the next step is we take this as a reference frame. Here we attach our reference frame. And now we try to calculate the position of the end effector within this frame, the red color, the frame that is attached to the joint 2. Okay, so what we do here, we apply the cosine and sine functions and we calculate x double dash and y double dash. But this time the angle beta is negative. So to find the, so we have a triangle here having this point, and then we have, so this point we call it here x dash, y dash here, the origin of this point, this reference frame. And then we have this L2, the main line, which is known. We want to find x dash and x double dash and y double dash. And what is unknown is still the angle with respect to positive x-axis. This can be calculated because beta is known and also alpha is known. So this angle is actually if you subtract angle beta from angle alpha, so you get the value of this angle here. Since beta is already negative, so we can just write it as this angle is alpha plus beta. Since beta is already negative, so this angle will be subtracted from alpha. So we now have a right angle triangle, and using trigonometry rules we can now calculate the value of x double dash and y double dash. So let's see. Okay, so now we have these two values, and you see that the final length of your end effector is along the y coordinates is the sum of your y dash and y double dash. So from here to here, this line this length is equal to, which is y, is equal to y dash plus y double dash. And similarly this length from here to here, which is x is equal to x dash plus x double dash. So it means we can find x and y if we know the values of the intermediate x's. So as we have seen already, x is equal to x dash plus x double dash and y is equal to y dash plus y double dash. So put the values of x dash and x double dash. X is equal to L1 cos alpha plus L2 cos alpha plus beta, and similarly y is equal to, we have L1 cos alpha, sorry, sin alpha plus L2 sin alpha plus beta. So this is how you can find the final position of your end effector. So this equation tells us that if L1 and L2 also the alpha and beta are known, then we can calculate the position of the end effector xy. So this is forward kinematics. And keep in mind that this method of finding the solution to forward kinematics problem, this is a, you can call it geometric solution. There are other solutions also which are more complicated and more like a generalized. So we shall study those types of solutions later in the upcoming lectures. Now let's see an example. So let we have L1 is equal to L2 is equal to 1, and then we have alpha is equal to 60 degrees, and we have beta is equal to minus 30 degrees. So these values are given, and you have to find the position xy position of your end effector. So using these formulas, what we have derived, let's see that we can find the x coordinate, which is L1 cos alpha, cos alpha plus L2 cosine of alpha plus beta. So putting the values here, x is equal to, we have here 1 cosine of alpha, which is 60 degree, plus 1 cosine of alpha plus beta. So 60 minus 30. So what's the value of cosine of 60 degree is 1 by 2 plus 60 minus 30. What is the cosine of 30? It's under root 3 by 2. So we can calculate the value of x, which is equal to 1 plus under root 3 by 2. And similarly we can find the y, which is L1 sine of alpha plus L2 sine of alpha plus beta. Y is equal to 1 dot sine of 60 degree plus 1 dot sine of 60 minus 30. So sine of 60 is equal to under root 3 by 2 plus sine of 30 is equal to 1 by 2. And if you add them, you get 1 plus under root 3 by 2. So this is where your final location of your end effector is when your angles are 60 degree and minus 30 degree and your lengths are equal to 1. Okay, now we shall try to do the reverse, which is the inverse kinematics. And keep in mind, this is a geometric solution. Or you can say geometric method to find the solution. And there are other methods also to find the kinematics and inverse kinematics. I think I should also mention for the kinematics also. Here I should write here geometric method. In later lectures we shall see some other methods also to find the forward and inverse kinematics. So again we plot our robot here. So we draw, since it's a planar two-dimensional robot having two joints. So here we have the x coordinate and the y coordinate, and here we have our origin having 0, 0. Yeah. So now let's draw our robot. this time we start from our end effector, which was somewhere here. This is the final position XY of our end effector, and we want to know that what is the configuration of your robotic arm, or what are the angles that the robot that results in this location of your end effector. So yeah, so let's say we don't know still the angles, and we assume that the angles are having any general value of angles. So this is joint 1, and here we have joint 2. Sorry, the link 1 and link 2. So this was here the joint 1, joint 2, and then we have link 1 and link 2 here. So no. Yeah, it looks better. Okay, so this is the robot, and now we try to. So here you see that the y coordinate, it can be so this is your y coordinate, and here is your x coordinate here. Considering this point for the end effector, so it has x and y coordinates. And what else we can do? We know that if we connect this point to the origin, we get a straight line. And we get also a triangle. We forgot to mention here we have the angle alpha, and here we have the angle beta. And this angle, the internal angle, this angle is, call it gamma. So this means that this angle, this internal angle, it will be (180 minus beta), because this angle is beta and the whole angle is 180 degree. So yeah, so if you see only this angle here, this angle will be alpha minus gamma. So again we consider this red triangle. In this red triangle, this is a right angle triangle, because here we have a 90-degree angle, and so this length that connects the origin to the point, we call it R. and we have a second triangle that is not right triangle. This connects your origin to your joint, to your second joint, and then to your end effector point, and then back to the origin. This is not the right angle triangle. Okay, so we have two triangles here, and the description of our robot is complete. So now it's time to do some calculations and try to find this angle alpha and this angle beta. The known quantities are L1 and L2 are known, and also X and Y are known. So let's see how we can calculate alpha and beta using geometry or trigonometry formulas. So the first thing we calculate is this value of R, because Y and X are known. It means we can calculate our R. So we can R. So R can be calculated because this is a right triangle. So we can calculate the value of R using this formula in this right angle triangle. So once the value of R is known, the second thing we can do is we can look in our second triangle, which is this one here, from this point to this point, and then to your end effector, and then back here. So within this triangle we can this is because this is not a right angle triangle, so we can use here cosine law to have a relation between the sides of the triangle and the angles of the triangle. Okay, so what the cosine law says that the cosine law says that a square plus b square minus 2ab cos theta is equal to c square. So means that within in this triangle here, the square of sum of its two sides minus the product and the cosine theta of the two sides is equal to square of the other opposite side. Okay, so this thing we try to implement it here. Okay, so for our case, the first one for R, because this was a right triangle here, right angle triangle, so we can use this formula. So remember, this angle was alpha minus gamma. This was a right angle triangle. This was your X, this was the Y, and this was R. So we said that X square plus Y square is equal to R. And then for your cosine law, we have this triangle. The internal angles are gamma, and this is R, this is L1, this is L2, and this angle is 180 minus beta. So yeah, so here when you want to make a relation between the sides and angles, you use cosine law. And if you apply here your cosine law, then you will get here something like so your A here is actually your L1, L1 square plus L2 square minus 2 L1 L2 cosine of 180 minus beta is equal to R square. So we have applied the cosine law on this triangle, and from here you can calculate you can write it down like cosine of 180 minus beta is equal to so L1 square plus L2 square, and then we have minus R square divided by 2 L1 L2. So if you want to find here beta, so your beta will be 180 degree minus cosine inverse L1 square plus L2 square minus R square divided by 2 L1 L2. So that's how you calculate your angle beta. So now we have calculated angle beta here, this angle. We want to now calculate angle gamma, because finally we want to calculate angle alpha, and we know that angle alpha can be calculated once we have this angle gamma. So yeah, so to calculate angle gamma, we need again to apply here the cosine law, but this time the central angle will be angle gamma, and the two sides will be L1 and R, and the opposite side will be your L2. Okay, so let's apply one more time the cosine law. Let's draw here this figure again. We have so this was L1, okay, so this was your L1, and then you have your L2, and if you connect these two links, then here you have your angle gamma, and this angle was 180 degree minus beta. This length was R, this was your L1, and then your L2 here. So let's apply cosine law here once again, and with central angle gamma. So again the cosine law says that a square plus b square minus 2ab cosine of theta is equal to c square. So L1 square plus L2 square minus 2L1 L2 cosine of gamma is equal to, no sorry, here it will be R so R square minus 2 L1 into R. The gamma and R look same. How to differentiate between them? Okay, is equal to L2 square. So from here we can calculate the gamma. So cosine of gamma is equal to L1 square plus R square minus L2 square divided by 2 L1 into R, and from here you can calculate your gamma. Gamma will be is equal to cosine inverse L1 square plus R square minus L2 square divided by 2 L1 R. Okay, so this is how we can calculate your gamma angle. So once we have gamma angle, then we can now go back to our main triangle here. This triangle, which was a right angle triangle, and here the gamma angle is known, x is known, y is known, and also r is known. So from here we can calculate our angle alpha. So let's draw this triangle again here, the right angle triangle. Alpha minus gamma, this was r, this was your y, and this was x. So we know that in a right angle triangle, we have tangent of alpha minus gamma is equal to y over x. So from here we can calculate our alpha, which will be tangent inverse y over x plus gamma. So yeah, so from here we know the value of gamma from here, and we just need to put it in the final equation. So your final alpha will be tangent inverse of y over x and then plus your gamma value, which is cos inverse L1 square plus R square minus L2 square divided by 2L1 R. So this is how you can calculate the values of your alpha and beta angle. So what was the value of your beta angle? Beta we calculated here. So it was 180 minus 180 degree minus cosine inverse L1 square plus L2 square minus R square divided by 2L1 L2. Yeah, so it means that we can calculate the value of alpha and beta angles if we know the location of your end effector. If you know the xy coordinates, then you can easily find the angle or this angle maybe, beta and your angle alpha. So these angles will be used by your controller, the controller that controls the position of your end effector, to maintain a error-free position of your end effector. So it will give commands to these motors attached to these joints to stay on these given angles. And keep in mind also that there can also be multiple solutions. For example, this position can also be obtained something like with something like this. So this is another different value of your beta and your alpha here. So yeah, so it means that there can be multiple solutions to inverse kinematics problem. So now let's see quickly another example that how we can find inverse kinematics. Okay, so what we have given is, we have L1 is equal to L2 is equal to 1, and the position of your end effector is xy, and this is equal to 1 plus under root 3 divided by 2, 1 plus under root 3 divided by 2. So this is the xy coordinates of your end effector, and what you need to do is find the values of alpha and beta using inverse kinematics. So here is the solution. First we need to to find alpha and beta. The first thing you need to do is, the first step is to calculate your R value, because this R length is common between these two triangles, the right angle triangle and also the other triangle on the left side of this R. So first thing is you need to calculate your R, and once your R is calculated, then you can calculate your angle beta. Okay, because here the L1 is known, L2 is known, and R you have already calculated, and then you can calculate your beta. So the solution is calculate R, which is equal to x squared plus y squared. So since the in the formula of the inverse kinematics, R square will be used, so here you see it's using R square, so we don't need to take the square root of the R. We can just use R square value. So instead of using the square root of x squared plus y squared, we can directly use x squared plus y squared. So our x value is 1 plus under root 3 by 2 square plus 1 plus under root 3 by 2 square. So which comes as 2 plus under root 3. So now we have R square, we can calculate the angle beta, and beta is equal to we have the formula for this one, and you see here 180 degree minus cos inverse L1 square L2 square minus R square. 180 degree minus cos inverse L1 square plus L2 square minus R square divided by 2 L1 L2. So if you put the values here, so it will be 180 degree minus cos inverse, this is 1 square plus 1 square minus 2 plus under root 3 divided by 2 into 1, and the final answer will be 180 degree minus cos inverse minus under root 3 by 2, and this equates to, let's do it on the other page. Here we have beta. Here we have 180 degree minus cosine inverse of minus under root 3 by 2. So this will have two solutions, either 180 degree plus (150 degree), or it can also be minus 150 degree. Okay, because if you take a cosine inverse of minus under root 3 by 2, it will give you either a plus value or also a minus value. Okay, so the final answer will be plus or either minus 30 degree. This will be your beta angle. Now let's compute the angle gamma. So gamma is equal to, we have already seen that, so gamma is equal to cos inverse L1 square R square minus L2 square. To L1R. Okay, so now we have these, we will put values here. Cos inverse, this should be 1 square plus R square minus square to 1 into R, and this will be cos inverse of R by 2, and if you take cos inverse of, put the value of R, which is equal to 2 plus under root 3 divided by 2, we get plus minus 15 degrees. Which is your value of gamma. So gamma can also have two values. Seem to like we have two values for beta also. So once we have calculated the value of gamma, then we just need to now calculate the value of alpha, and we So we have that alpha is equal to tangent inverse of y over x plus gamma. Tangent inverse of, because y and x both are 1 here. You see we have they're not 1, but their ratio is 1. So they have same values. This is x and this is y. Okay, and when you divide them here, when you put them y over x, then you will get same value. So let me put it 1 plus under 3 by 2 and then we have plus or minus gamma. So this will be equal to 1. So we have here tangent inverse of 1 plus minus, put the value of gamma, it's tangent inverse of 1 is equal to 45 degree plus minus the value of gamma is, we have 15 degree. So which is equal to 60 degree or 30 degree. So as you have seen that there are multiple solutions for every joint angle. For alpha we can have a value of 60 degree or 30 degree, and for beta we can have either a value of plus 30 degree or minus 30 degree. So that's what I was previously explaining, that we can have multiple configuration of the robot to reach us for the same position. Okay, so we have calculated the alpha can be either 30 degree and also it can be 60 degree, and similarly beta can be either minus 30 degree or also it can be plus 30 degree also. Though this is not accurate representation, but it's a rough one. So yeah, so this is inverse kinematics. This is how we solve problems using inverse kinematics using geometrical methods. And keep in mind that there are also other methods. We shall find them later. We shall study them in upcoming lectures. So thank you very much for listening. If you have any questions, please feel free to contact me by email, and have a nice day. Bye.